In the homework, people generally did well, but one thing I wanted to point out to you, we had some relationships between the transfer function, right, and the impulse function. So, for example, we discovered that the transfer function is, in fact, the Fourier transform of the impulse function. This means it can be written this way. I don't need that. With the E minus I omega t dt, and therefore the impulse function can be written as 1 over 2 pi minus infinity of transfer function e to the plus I omega t d omega. Okay? Right. So, and in the homework, the last two homeworks, we originally determined the transfer function by looking at sinusoidal inputs and sinusoidal outputs, right? And then I said, this is the definition of the impulse function. Can't argue with the definition. Well, you can, but it's hard to argue with the definition. So there's that. And then I said, but appealing to the idea of an inverse transform, then the transfer function can be written this way. So what I asked you to do is take the transfer function to determine the sinusoidal inputs and outputs and compute this. And eventually everyone recognized that if you look at the right integral table, you could perform those integrals. And then I asked you to go, okay, take that, put it back in, and reconstruct the transfer function. The key to doing that, some people struggle with the key to doing that is to recognize that when you do this, you can put the lower limit to 0. In fact, it's essential because two reasons. One is this thing is 0 for t less than 0. Okay? And if you try to integrate from minus to plus infinity, you get nonsense. And the other thing is, I forgot exactly what the impulse function looks like now. It's somewhere in the official homework. But basically, it's some constant and then a sign of something. And then it's exponential to a minus something times t. You see, this is the thing that's going to make it die off at infinity, right? And this fact is going to make this integral die off at infinity. So when you integrate this, which you can, since that these are just simple exponentials and signs, you're basically going to get an analytical answer, and then the contribution at infinity is going to be 0, right? And the contribution at 0 is the whole story. So that's important to know. So important to recognize that this thing is 0 for t less than 0, and that this makes this integral well behaved. If you had a function that didn't die off in time, and you tried to do this integral out to infinity, you have to think about things like delta functions, right, and other singular functions that make sense of what the integral means. Okay, we still don't have anybody in softball, right? No, well, it's their loss, I'm sure. Two other things I want to do today. One is give you the opportunity to ask questions about the new homework. And Dan, if they're easy, I'll answer them. If they're hard, Danny will handle those. But this is not the last time you'll have a chance to ask questions. You have now almost 2 weeks, including the holiday, to work on this. Charlie deserves a lot of credit for lobbying me. They give you an extra week. Right? So not only is he benefiting, but all of you owe him big time. I just want you to know that. But if you have any questions about the new homework, or you've not thought about it yet, you're worried about where you're going to go on spring break and more important matters, right? Do you need a visa to go to Spain?
Early honeymoon to Spain.
Oh yeah, okay.
To Lisbon, Portugal for a long layover, so a little stop there, and then Seville, Cordoba, Madrid, Zaragoza, and Barcelona.
Okay. I've never been to Spain. I've been to Lisbon 3 or 4 times. Lisbon is great. And you're not taking the time, but if you go to the south of Portugal, to the coast on the Mediterranean, that's fantastic too.
One day.
You can take a train out of Lisbon down there. You can do a day trip down to the Algarve. And it's mainly German beer gardens and British pubs. But they also have some pubs, some coasts. The northern Europeans love Portugal because it's beautiful weather and it's relatively inexpensive. Yeah. Americans love it too. Yeah. And you know about the fado?
No.
The fado is the indigenous. Tell them about the fado. We have a citizen of Portugal with us. Yes.
It's just sort of sad songs that people they wail.
Yeah. You're obviously not a fan.
You're really selling it.
Yeah, you really. Don't overdo it. Don't show too much enthusiasm.
It is fantastic. You have to be in a very
yeah, you have to be in the right mood. If you're into music, it's a combination of opera and the blues. Think of the opera plus the blues. Think of that combination. That's what the fado is.
I can't even begin to imagine.
Well, you go to a very nice restaurant. You have to save up your money. Go to a very nice restaurant, and they'll have 3 or 4 groups. One will sing with the appetizer, one will do the entree, and one will do the dessert. In fact, I went to a very nice restaurant in Lisbon, and I was going to leave. I was going to have dessert. So no, the best group is the one that comes and sings with dessert. So I had dessert. And it was the best group, but they were all good. Okay, questions about the homework? New homework? No. Okay, now we're going to have, in 1 hour, a summary of all that you need to know about classical unstudied aerodynamics. But if you want to know a few of the details, what you should do is take what I'm about to tell you. Read chapter 4, because I describe it as well as I'm capable of doing it in chapter 4. And then come to the rest of the lectures for the rest of the semester and ask questions. Right? And I'll assign some homework about it too. Okay, let me ask you this question. I know the answer is yes for some of you. How many have taken Professor Bliss's course in acoustics? Good. How many are thinking about taking that course in acoustics? Well, it's your loss. How many of you have taken a course in acoustics from anybody at any time? Same 3 people? Okay. All right. Unstudied aerodynamics is just acoustics in a moving coordinate system. That's all it is. But it makes all the difference because unstudied aerodynamics is mathematically much more elaborate than acoustics. But some of the basic physical ideas are still the same. So we're going to start with acoustics and then move to the moving coordinate frame. In acoustics, well, first of all, they're all based on some basic ideas in fluid dynamics. But fluid dynamics is just like dynamics of any subject. You have to think about conservation of mass, which is sometimes you don't really think about with a solid because you think, the mass is always there, it's not going to change. But with a fluid, if you think of a glob of fluid and there's fluid coming into that volume, like this room, there's fluid coming in the door, and then maybe there's some fluid going out the door, right? And then there's fluid changing inside. So if you look at a so-called control volume, say the volume of this room, you have to think about the mass coming in, the mass coming out, and the mass change in the room itself. So you have to write down conservation of mass. Then you have to write down F equals MA, or as the fluid mechanicians would say, pressure acting, perhaps shear stress, but usually just pressure in classical aerodynamics, acting on the volume of fluid, and that gives rise to acceleration. But then often you want to write acceleration in the moving coordinate frame. We'll find out why in a little bit later. And then what that will do is that will give you basically 2 equations. Conservation of mass is a scalar, so that's one scalar equation. F equals ma is a vector equation, right? So you have one vector equation, one scalar equation, which equals the equivalent of 4 scalars. you have density of the fluid, and you have the two components of fluid velocity, plus you have pressure, even in an inviscid aerodynamics. So you have 5 unknowns and 4 equations, and so you got to do something about that. So you appeal to thermodynamics, which gives you a relationship in isentropic processes between pressure and
Hello, we are hearing now.
scalars, 5 unknowns, 5 scalar equations, and you're in business. Except those are nonlinear partial difference equations, even for inviscid flow, and therefore not solvable analytically. And so it was only with the advent of the age of computer that people really began to solve those equations in a serious way. And that's the whole field of computation.
Hello, we are here now.
Now, if you have the
We are hearing.
you have to add at least one unknown, more unknown, namely temperature, and you need one more equation. Usually it's an energy equation. So then you're 6 equations in 6. Classical aerodynamics usually ignores viscosity, which turns out to be perfectly adequate to find the pressure on a body moving a fluid in 99.9% of the cases. But the 0.1 are important. Where's not workable. So classical aerodynamics is still what people mostly use to do aeroelastic analyses, even in the year 2017. And that's what we're going to discuss. Okay. Now, you take those equations I just mentioned and boil them down, and you assume that there's a mean flow, which is uniform. This is an approximation, right? But think of a wind tunnel. There's a mean flow with a mean velocity, and then you assume that, and that it also has a mean temperature and a mean pressure and a mean density. And then you assume that if I put an object in there, like a wing, whether it's moving or not, it gives rise to a small change in all those parameters, right? So you assume that the pressure is, if you will, the static pressure far upstream of where the object is, plus a perturbation. And then you try to find the equations that govern that perturbation. And if you ignore viscosity, you ignore changes in entropy, if you remember what entropy is, and you assume an isentropic process, voila! The equation for the perturbation pressure is the following. It's Laplacian acting on the pressure perturbation minus 1 over the speed of sound. This is the mean speed of sound, right? It's 343 meters per second at ambient conditions, times the second time derivative of the pressure equals 0. And this is an equation which is written in the coordinate system fixed with respect to the flow. So it's what I'll call the flight coordinate system rather than the wind tunnel coordinate system. See, I'm out in there, I'm sitting on my cloud, and the airplane is coming by, right? And when the airplane goes by, it disturbs the fluid and gives rise to this perturbation and pressure. And if I'm sitting on the cloud and I'm in the fluid fixed coordinate system, this is the governing equation, the sum approximation. If I'm sitting on the airplane, then I'm in a different coordinate system, and that complicates this equation. And it complicates it in the following way. Capital D is usually called the substantial or convective time derivative. It's the ordinary time derivative plus u infinity, that's the speed at which the airplane is moving, times d dx, where x is the coordinate in the direction in which the airplane is moving, right? We align the x direction with the movement of the overall movement of the airplane. So this is a vehicle fixed coordinate system, and this is the fluid fixed coordinate system. And you can move from one to the other by writing down the relationship between the coordinates in the two coordinate systems, and then doing a coordinate transformation. That's a great homework question. It's also a great question to ask on qualifying exams, and final exams, and other exams, right? One of the standard questions that you get asked. Now, for the most part, we're going to deal with this equation. We're going to be dealing with the vehicle equation rather than the fluid physics equation. By the way, this fluid physics equation is exactly the equation that you use in classical acoustics, right? Because if I'm saying the fluid physics coordinate system, it's acoustics with a body moving through the fluid, right? So then the question is asked, why in the world would I ever use this equation, which is obviously more elaborate, if nothing else, than this equation? Why would any sensible person do that? The answer is
Because it works.
I'm sorry?
Because it works.
Because it works, yeah. But yeah, that's true. That's very true. But let's peel back one more layer. Why does it work better? I mean, you can do it either way in principle, but this is better. The answer, You can measure it. No, yeah, if I had my microphone on the vehicle, I mean, I could put my microphone on the cloud and measure it, or I could put my microphone on the surface of the vehicle. Now, it is true, it's a little more practical to put it on the surface of the vehicle than put it on the cloud. That's true. Although I could think of, well, yeah. Anyway. The reason is I have to solve this partial difference equation for pressure. But in every partial difference equation, there's some other data that I need to solve that equation. And what are they? They are what? Initial conditions, yes. And what else? Boundary conditions. Where's the boundary? Well, there are actually two boundaries. There's one at infinity, and there it doesn't, it's infinity. Who cares whether I'm in one coordinate system or the other? But the other boundary I have to worry about is the boundary at the interface between the vehicle and the fluid. And it's a lot easier to apply that boundary condition if I'm in the coordinate system that's fixed with respect to the boundary itself, right, the vehicle. So it's all about trading off the ease of applying the boundary condition by using this equation versus having a more complex equation. In fact, for this equation, what equation is this? Is one of the most famous equations in all of partial difference equations. When you take a course in partial difference equations, there are basically three equations that you study, and they are. Which one? Wave. This is the wave equation. What are the other? That's true. What are the other two equations? Don't remember. Oh, well, that's one. You got one out of three. In baseball, you can make a lot of money by getting one hit out of three. Not in engineering, though. We have higher standards. Which one? The heat diffusion equation. Heat equation. Very good. And the third one is. Laplace's equation. Very good. By the way, if I eliminate that term, or this term, it is Laplace's equation. So when this term goes away, it is Laplace's equation. So the wave equation, in some sense, includes Laplace's equation if you let the speed of sound go to infinity. I.e., if the vehicle velocity is much lower than the speed of sound, then I can throw away this term and it's Laplace's equation. So incompressible flow, low-speed flow, is governed by Laplace's equation. Well, what about the heat equation? Actually, the heat equation enters in too, but not within this framework. It turns out when you're in low speed, as we'll see, low speed is Laplace's equation. It turns out in supersonic flow, it's mostly a wave equation, okay? And in transonic flow, it's the transition between Laplace and wave, and that turns out to be something that looks sort of like the heat equation. In fact, mathematicians talk about elliptical equations, i.e. Laplace, hyperbolic equation, that's wave, and parabolic equations, that's in between, that's heat. And if you look at the Navier-Stokes equations, you see a comparable, it's a more elaborate, a comparable transition of Navier-Stokes. So fluid mechanics has all the classical PDEs buried in it, and depending on what speed range you're in. Okay, that's good enough. Now, the solution to this equation under certain circumstances gives you piston theory. Okay?
Take your word for it.
No, don't take my word for it. You're going to say, how is that? How is that, Professor? I'm glad you asked that question. I'm going to tell you. How is it? I thought we rehearsed this. You didn't cooperate. Okay. So let's talk, Adam, your homework. Okay, let's talk about where piston theory comes from. First of all, let me describe why it's called piston theory. And this goes back to acoustics, okay? If I have a channel and I have an object at the bottom of the channel which moves back and forth with some displacement, that's called a piston. It's, at least there's one version of a piston. So this is a piston. And then if I want to know the pressure on the face of the piston, I have to solve a suitable equation. And if I think it's governed by the equation of acoustics, that means I'm going to call this suggestively the Z equation, Z direction. That means this equation I need to solve this equation, but it's basically now one-dimensional. So this Laplacian just gets replaced by, I'm assuming nothing's changing with respect to X and Y because this is such a narrow channel. All the changes, all the significant changes are in the Z direction. Good morning, Stockholm. Great to see you. I'm not sure when you came into the
Good evening.
Okay, we're talking.
Can you hear us?
Hello?
Hello.
Yes, good. We're talking about unstable dynamics.
Nice.
And your assignment for the next 2 or 3 days is to read all of chapter 4. So this is an introduction to help you read chapter 4 with some greater understanding. Okay, so I want to solve this equation subject to some boundary conditions. Okay. And maybe some initial conditions too. So how shall I do that? Well, why not? I mean, there are lots of ways. Let's use separation of variables. So this is a function of Z and T. So I'll assume that this is some function capital Z of Z. Notice the wonderful notation here. Capital T of T. We can certainly do that. And if we put this in here, what might we attain? We will attain, I'll use this notation, Z sub ZZ. That's the derivative of this function twice with respect to Z, right? Times T minus 1 over speed of sound squared, Z times T of dt equals 0. And then what else did we do? Thank you. Well, we separate variables. That's what you told me to do, right? So this is Z over ZZ, Z sub ZZ over Z equals T sub TT over A infinity squared T. This is only a function of Z, and this is only a function of time, and therefore we conclude that these ratios must be constant. Thank you. And let's see, I've done this before. So I want to make sure it comes out right. I always have to think about what the sign. Well, let's just. I've forgotten what the sign should be, so we'll just choose a sign, and if it's wrong, we'll come out of the analysis, right? So what do you want to call this constant? Just call it C. Okay. All right. So then I now have two ordinary differential equations in place of one PDE. That's a good trade. Why? Because ODEs, even though they're twice as many, are easier to solve than PDEs. In fact, the only way to solve a PDE analytically is to convert it into an ODE that I know of. I mean, there are various methods for doing that, including taking a Laplace or a Fourier transform, by the way. But you said separation of variables, and I'm going to go with your suggestion. Okay, so we have now Z sub ZZ minus CZ equals 0. That comes from using this and this, right? And then T sub TT minus C. Did I do that right? Yeah, I think I did that right. Oh. T over A infinity squared equals 0.
It should be times A infinity squared.
I'm sorry?
It should be times A infinity squared, not over.
Oh, you're right. Thank you. That will help. That will help. Okay. Now what are we going to do? Well, we can solve these equations, right? What's Z equal to? Z is equal to, it's going to be some constant, call it C. Oh, no, I don't want to call it C because I've used C for that constant. I'll call it A. A e to the plus square root of CZ plus B e to the minus square root of CZ, right? I mean, if I want to do this formally, what I do is I assume the Z is e to the lambda Z and figure out what lambda is, right? But I think I did that, right? Because if I differentiate this twice, I'll get a factor of C here, right? Oh, excuse me, up here. And I'll be okay. If I differentiate this twice, I have a minus sign each time, but they'll come back to a plus. So I got that, right? Okay. And for simplicity, we could put another wall up here, if you will. That would be, in aerodynamic terminology, the wall of the wind tunnel. But I'm going to let this go out to infinity, because I want to think about the boundary conditions that might apply to infinity. And infinity, what do I want to have happen? I mean, what does this solution do at infinity when Z gets very large? It what?
Blows up.
Blows up. Now, this is presuming that C is a positive constant, by the way, if you notice carefully. But let's assume that. If it proves to be wrong, we'll get in trouble and have to do something about that. So I'm inclined to throw this away based on the physical argument that my solution must be finite at infinity. So, and I'll retain this solution. Okay? I'll retain this solution. But now I still need to find B. So how are we going to find B? Let's see. This is 5, 6, 7, 8. Well, I've got another boundary condition on the face of the piston. I'm presuming that someone is telling me how the piston is moving. I'm an aerodynamicist. It's the structures person's job to tell me how the structure moves, right? I just do aerodynamics. I don't do structures. And there are people in the aeroelasticity group who have that point of view. And it's okay as long as someone above them knows how the structure and the aerodynamics come together. Okay, so let's think about that then. So we've got what? We've got Z now is equal to B e to the minus square root of C times Z. And then, of course, we've got T minus C A infinity squared T equals 0. So this is 8, and I've just rewritten 7. Okay? All right, so let's now look at the boundary condition strictly speaking, it's on the face of the piston is moving, but the piston motion is small enough. I can say it's essentially at Z equals 0, right? Z equals 0 is where the piston was before it began to move. Now it's moving a little bit, but just a small amount. So we're going to think of the boundary condition being applied not on the face of the piston, but at Z equals 0. If you want to do nonlinear ancillary dynamics, then you have to actually apply the boundary condition on the face of the piston, which usually means you're going to do some sort of numerical procedure. But if you're striving for some sort of analytical solution, you allow for small motions. So what's the boundary condition on the face of the piston? Well, it's that the fluid velocity, and this is in physical terms, the fluid velocity equals the piston velocity on the face of the piston. So if Z sub P is the displacement of the piston, then ZP dot is the velocity, right? Dot means derivative with respect to time. This is the velocity of the piston. Okay. I need the velocity of the fluid, right? And I need to relate that to the pressure. That comes really from Newton's second law, but in the context of fluid dynamics, it's usually called Bernoulli's equation, because Bernoulli was the guy who took Newtonian mechanics and applied it to a fluid and got the relationship between pressure and velocity. Okay. And to do that, he introduced an additional concept called the velocity potential. So we need to make a side excursion here to talk about velocity potential. Concept of velocity potential. In this case, the name actually is fairly well chosen. If I take the gradient, i.e. a spatial derivative of the velocity potential, I get the fluid velocities. So d phi dz, we're going to call the velocity potential phi. Note that we've used that also for correlation function, but you will never get confused, ever, between phi, which means a correlation function, versus phi, which means velocity potential, right? There are only so many letters in the alphabet, so you got to accept the fact that sometimes the same letter is used for different meanings. Anyway, d phi dz, then is the velocity, fluid velocity in the z direction. D phi dx, which we don't need to worry about yet, but I'll just point this out, and d phi dy are the velocity components of the fluid in the x and y direction, right? And Bernoulli became famous for finding out that the pressure perturbation is equal to the mean density. Remember, piston theory involves the mean density, so here's where it comes in our story, times the time derivative. And by the way, these are all perturbation. We're always talking about perturbations now. This is true for the total velocity as well. Dt. Okay. So this is Bernoulli's equation, or one version of it, from Newton's second law. That's where it comes from. So now what do we got? 9 is just the definition of the velocity of potential, of the velocity of the piston, rather. We've introduced the concept of velocity potential, and 10 will be Bernoulli's equation. Okay. With all of this together, then the boundary condition at z equals 0 is that the velocity, perturbation velocity in the z direction at z equals 0 must be equal to zp dot, right? That's the boundary condition. So now I have a boundary condition involving phi. I've got obviously using Bernoulli's equation converted into the boundary condition involving p, because that's what I need to evaluate that constant. But we can do this, I hope. We'll see. If it doesn't work, it's Kevin's fault, right? But he's the one that suggested we do it this way. I would have used Laplace transforms myself, and which is what we do in the book. But you told me to do this.
It will work.
So this is going to be interesting if it works out. Okay. So now let's just repeat what we have here. What do we have? We have now capital Z. That's our B e to the minus square root of c times z. Okay. What else? That's equation 8. We have the boundary condition. Oh, I'm going to give the boundary condition of an equation number. I'll call that 11. We have the relationship between pressure perturbation and I'm just quoting this result. I'm invoking higher authority here. I'm saying if Bernoulli said it's true, then Daly is true, right? That's Bernoulli's equation. And then, of course, we have the boundary condition itself in terms of velocity potential. Okay. Now, we have a couple of possibilities here. We have an expression for P. We have an expression for Z. We haven't determined T yet, right? Remember capital T as a function of time. We can, from 8 and 10, and also the definition of T, we can find an expression for phi and then apply the boundary condition, or we can take this boundary condition and use this equation to convert it into a boundary condition on P. Right? I mean, with that, I'm thinking out loud because I haven't done it this way before. But I have those two choices. I think I want to convert it into a boundary condition on this into a boundary condition on P using Bernoulli's equation. Okay? I mean, you do it the other way. Well, that'd be a good homework problem. Yeah, I'd do it the other way. Good idea. Okay, I'll do it this way, and we'll leave the other way for a homework problem. Okay, so what we've got here, we've got d phi hat dz, but P is related to d phi hat dt, right? Now, this is evaluated on z equals 0, but both sides are still functions of time in general, right? So I can differentiate 11 with respect to time, right? And I'll get second partial with respect to t and z equals zp double dot. Again, this is evaluated at z equals 0, right? Now, why would I want to do that? Well, now you see, I can differentiate 10 with respect to z because we haven't set z equal any particular value, right? And so if I do that, then I'll get dp hat dz equals minus rho infinity second derivative of phi hat with respect to z and t. Now, I'm going to make a bold assumption that a mathematician would worry about, but I'm not going to worry about it. And that is, I'm not going to worry about the fact that the order of differentiation with respect to z and t matters. I'm going to assume that everything's smooth enough that either way is okay. So now I'm going to use this and write this boundary condition, write this. I'm going to take this, if you will, I'm going to solve for this in terms of this divided by that and put it in here, right? I can do that. So I've got minus 1 over rho infinity dp, thank you, dp hat dz. How am I doing?
Oh, sorry, you wrote that. There you go.
Evaluated at z equals 0, which is equal to this, right? But that from the boundary condition is equal to zp double dot. Okay. Okay. Now I need, so this is all, where am I? I'm in 12. And now I need to replace p hat by, what is it? P hat is equal to capital Z times, recall, right? But that is equal to T times B times E to the minus square root of C times small z. Okay. That seems to be working nicely. And now I need to differentiate this with respect to z. So that's whatever it is. It's t b minus the square root of z e to the minus square root of z times c, right? But for the boundary condition application, I can set z equals 0. So this goes to 1. And I have t b minus the square root of c times, that's it, I guess. And I get all this, and then I have a minus sign here, and I divide by rho infinity, and that's equal to zp double dot. Okay. 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 So I've got that. So I've got 13. So, and then recall, we also know something more about t. We know that t obeys this equation. Okay, and that's equation. What was that equation? 9. Yeah. Okay. So we're making progress, but we're not there yet. This is a hard way to do the problem. Okay. Well, we're going to keep going. Okay. So now I'm going to write these one more time. and T okay, this is 9. So let's now work on 9 for a bit. I think that's what I want to do next. If I solve this equation for 9, what do I get? I get T equals, I guess I get use of, I use A and B. Don't want to use C. I'll use E and F. Okay. E to the minus, oh, this is squared, right? Minus the square root of C, A infinity, T plus F e to the minus square root of C, A infinity, plus T. Okay. Okay. Now I have to evoke some initial conditions, I think. All right. So let's try some initial conditions. What initial conditions would you like? I'm going to choose, I'm going to say initially everything's quiescent. So P hat is 0 at T equals 0. Okay. And what else? I'm not sure if I want to make P dot 0 or not. Let's try that. We'll try it. We'll say this: the piston is not moving initially, and it doesn't even have any initial velocity either, right? So I'm gonna try P hat dot equals 0 at T equals 0, but I may get in trouble doing that. So I'm gonna put a question mark there. Now let's look at these solutions. I've got a solution. If C is really a positive constant, I've got a solution that's blowing up. And here I got one that's decaying. So if I use the same logic as before, presuming that C is a positive constant, I probably want to throw this one away. But then I think, gee, I'm an aeroelastician. When solutions blow up, I'm fascinated with those solutions, right? Am I throwing away too much? So I think the other thing I would conclude is that C is probably a negative number. And these represent oscillations in time.
So we see it's negative.
Yeah.
Throughout the term.
Yeah, that's right. So we have to go back to our assumption about C too. See, the danger is I know the answer. You really have waves. This is a wave equation, right? You really have waves. It turns out the C is going to be a negative number. Okay, but if you weren't aware of that fact, you probably go through what I've just gone through and come to here and then say, I think I'm getting in trouble, right? And so you would then, I hope, go back and think, well, maybe some assumption I made along the way isn't the right assumption. So now it appears that, it appears that C is less than 0. Okay? Okay. So then this solution, which I'll call, we're up to 14 now. 14 is really this. T equals, I'm still going to use E and F, although strictly speaking now there are two other constants that doesn't matter. E to the minus I, I'm going to define now C as minus C star, I'll call it C star, minus square root of C star A infinity T plus F e to the plus I square root of C star A infinity T. But since these are arbitrary constants, which I have yet to determine, and I know that a complex exponential is just a cosine plus an I sine, right? I can also write this, and I'm still going to use E and F because I only have so many symbols, and I have to determine anyway, they're arbitrary constants, right? I'm going to write this as E cosine square root of C star A infinity T plus F sine square root of C star A infinity T. Right? So I can do that. Okay, but now that I've done that, I still haven't applied the initial conditions, by the way, right? I still haven't done that. Now let's go back and think about what we need to do about Z. Remember? Recall Z we assumed was what? We assumed that Z was A e to the plus square root of C. This is I think you can still read that. Well, let me know. Recall we did this. We had what? E plus square root of C Z plus B e to the minus square root of C Z, right? But now we think this really should be written A. I'm still going to use the same arbitrary constants, right? Because I'm going to go back and rethink my boundary condition too. E to the plus I square root of C star Z plus B e to the minus I square root of C star Z, right? Okay. And this is going to be 15. Okay. That's good. Excuse me, this is capital Z. I want to make sure you say that. But now, remember before I threw away one of these solutions based on one of them being finite and one of them not as Z gets large. Both of these are finite. But I've only got two boundary conditions to determine A and B, and one of them's an infinity and one of them's on the face of the piston. So I need a new boundary condition other than finiteness. I need to say something else. Okay? And what I'm going to say is that I will interpret the solution I've obtained now that I've got these oscillating in C and T as waves. This is the wave equation. And physically and mathematically, there's one wave that's going to start near the piston and go out towards Z equals infinity. And there's another wave that starts at, according to the mathematics, that starts at infinity and comes towards the piston. And I claim only one of those is physically possible, namely the one that starts at the piston and goes out. There's nothing at infinity, as far as I know, more than anyone on the cloud, that's going to create a wave that will move in toward that, right? Okay. All right. So, with that in mind, let's go back to earth, fire, wind, and water. We now have concluded we have solutions of the form for P hat. They go like E plus or minus I square root of C star times Z, right? That's the dependence on time, on Z, times E plus or minus square root of C star times A infinity times time. All right? Those are all the solutions that we have. And so if I collect those, I've got E, I've got an I, I've got Z plus or minus A infinity times time times the square root of C star. Okay. So, of all these possible solutions, which ones do I want to retain and which ones do I want to throw away? And this really comes down to the choice of the plus or minus sign. So which one do I want to keep? Which one represents the wave going out? Which one represents the wave coming in? You have a 50-50 chance of getting it right? We have a one vote for positive. Is that one going out or coming in?
Going out.
Going out. You like that one going out. Any other people who would like to offer an opinion?
Obviously, Danny is wrong. Obviously, it's negative.
Okay, we have a vote for negative. That's good. We have a vigorous discussion. Okay. Well, we're waiting for you're both very brave, and I appreciate that. What about the rest? Yeah, Adam. Negative. We have you're getting outvoted at least temporarily. What about what? You're saying negative. 3-1. It's not looking good for you then. Anyone else? You've got negative?
Yeah.
Okay, 4. All right, that's well. Often in science and engineering, the majority is wrong. But in this case, you're right. But now the question is, why is it the minus sign? Yeah. The wave is defined by the combination Z minus A infinity T remaining constant as Z and T both increase in value, right? And so if they're to both be, think about it, as T increases, Z must increase also in a positive sense for Z minus A infinity T to remain constant. So Z minus A infinity T represents the outward wave. And conversely, the plus sign represents the inward wave, because as T increases, Z must decrease for the combination to remain the same. So what we know now is that P star goes like E to the plus or minus Z minus A infinity T, there's an I, and then there's a constant we don't know yet, right? But we're getting there. We're getting there. It's a hard way to solve a problem, Kevin. I can't believe you told us to do it this way, but we're going to do it this way. So this is 16. So we've applied what I'll call the outward wave condition. But no one else calls it that. People call it the radiation condition because this was originally done in electromagnetic radiation theory, right, using Maxwell's equations. So this is really called the radiation condition. But you think of the wave radiating outward, right? Radiation condition. And if you really want to impress your friends that the next time you're having a beer, you call it the Sommerfeld radiation condition, who was a famous German physicist that worked in electromagnetic radiation theory. So this is called the Sommerfeld radiation condition. But notice that we're invoking some physics here. I mean, we've got two solutions and two boundary conditions, and we need to make sense of it, and this is what they came up with, which proves to agree with experiments, so maybe it's okay. Okay. So now we have P hat. I'll put another constant out in front. Like so forth. Yeah. Z minus A T square root C star. Okay. Call it 17. Now, yeah, I think we're going to be okay. Okay, recall our boundary condition again. Where were we? Few pages ago. This is equation 12. Minus 1 over rho infinity dp hat dz at z equals 0 equals zp double dot. Right? That's what we had. So let's compute the dp hat dz now. It's a e plus or minus I z minus a infinity t square root c star times the coefficient of z, which is plus or minus I c star. And then we're going to evaluate this at z equals 0, right? And so that's going to be a plus or minus I square root of c star e plus or minus I z minus a infinity. Oops, the z isn't there, right? Thank you. Thank you. Running out of room here. Equals ZP double dot. We're going to get there, I think. Now, we need to know what C star is, right? We need to know what A is. And how we're going to determine that in terms of ZP double dot. And I think that's going to be hard, actually. But we will attempt it. So we have A plus or minus I okay. And so let's go back to our original equation. This is, on page 7. This is the longest derivation in history, I think. We'll go back to our original differential equation. And of course, we want our solution to satisfy this differential equation, right? So, and our solution so far, it has some unknowns in it. It's A and all this stuff. Okay. So we're going to take this and put it in here and see what constraints are applied to our solution. Clearly, there's not going to be a constraint on A, right? Because it's all going to, it's a linear equation, the A's are all going to cancel out. But maybe we'll have a constraint on C star and we can determine C star. So let's see if that's possible. So it doesn't matter we have, well, it really doesn't, well, there's an I here, right? So let's see. If we differentiate this with respect to Z twice, we're going to get C star, because the square root of C star squared. We'll have plus or minus I squared. And then we'll have minus 1 over A infinity squared. And then we'll have the I will give us a C star again. I'm missing something here. We'll have this plus or minus I squared. And we're going to have, now we're just going to get an identity, right? Because then we're going to get this squared too, which will cancel out that. So this is going to be identical to 0. That's going to help us.
The boundary condition will give us information about C star.
Say again?
The boundary condition, because this is
Well, but I was going to use the boundary condition for something else. But let's try it. Let's try it. Let's go the other way. The boundary condition gave us this result, right? But it doesn't really tell us anything about C star that I can see.
This initial function can be sine or cosine, and based on the orthogonality, the right hand side can be either just a sine cosine function or Fourier series. Either way will give us some information about the frequency.
Well, let me cheat a little bit, and let ZP have a certain time dependence. Well, no, that's not going to help us either, I don't think. See, all we've done so far is we've proven that our solution is some function of Z minus A infinity T, right? I mean, that's all we've known. The general solution is that plus this one, but we're throwing that away because of the radiation condition. Yeah. So let's try that, and then maybe that will help us. If we now put that in this differential equation, if I differentiate this, if I define this combination of Z minus A infinity T as some variable C, right? Then I can, if I do that, and I take this equation, it's almost 18, 19, and 20. If I take this result using this definition in here, I'm going to get F, I'll call it prime, where prime denotes derivative with respect to C, minus 1 over A infinity squared. Well, that's just going to prove the same thing, right? This is going to give me an identity too, which is nice, but doesn't help me. Okay, so let's take this and use the boundary condition. I have dP minus 1 over rho infinity dP dz equals ZP double dot. Maybe that will help us, because I really wanted to find out what this function is, right? So this tells me that minus 1 over rho infinity df just one derivative. Df dz at z equals 0 equals, I think I'm going to get it now. Finally. Okay. Yeah. This will do the trick. Minus 1 over rho infinity dp dz equals zp double dot. And that will tell me that minus 1 over rho infinity df dc at z equals 0 equals zp double dot, right? But c, recall, is this variable c minus a infinity t. Thank you. Okay. And I could instead define a variable eta, which is t minus z over a infinity, and it would still be true that there would be a new variable f, which would go like this. Okay, so then I would have minus 1 over rho infinity df d eta at z equals 0 equals zp double dot. But that's like minus 1 over rho infinity eta. If I differentiate respect to z, I get a minus 1 over a infinity times f prime, where prime is derivative with respect to eta, okay, equals zp double dot. But if I apply this now to z equals 0, that's like differentiating this with respect to time. And so now I have 1 over rho infinity a infinity df dt equals zp double dot. And now I integrate that once with respect to time, and then I have f equals rho infinity a infinity zp dot, which is essentially pressure. And this is the pressure evaluated, by the way, on z equals 0, right? That was hard, Kevin.
Sorry.
Okay, you'll be happy to know that in the book, we take a Laplace transform with respect to actually time, and you can reproduce this in one page. So I wouldn't recommend this derivation, but at least we got the answer. By the way, you'll notice that there's a plus sign here. Why is that? Because the way we did this, the pressure is acting on the face of the piston, so the pressure is acting down. On our airfoil, there was a minus sign because there's a pressure on the bottom and a pressure on the top, and when you put the airfoil at a certain velocity, the net pressure is up with the minus sign. So that there's a minus sign you have to think about too. That was a struggle. I'm never going to do that again. Boy, next time I have somebody to tell me how to solve the problem, they say separation of variables. I'm not going to do it that way. Yeah. Okay, sorry about that. It took so long. Okay, so next time, this is the last meeting before the start of the break. After the break, we are going to start doing chapter 4. What we'll do is we'll do a brief derivation of the wave equation starting from earth, fire, wind, and water. And then we'll do supersonic flow using transform theory, not using separation of variables. And then we'll do subsonic theory. And then I think there'll be time to at least touch on on transonic theory. Stockholm, have you hung in there all this time with us?
Yeah, we are here.
Well, I'm happy to hear that. And I hope you appreciate the great effort that Kevin and I made to derive piston theory using this separation of variables technique.
Yes, of course. Thank you.
Very good. Okay. Any questions before we break up? No. All right.